Go ahead, William, with unsupervised brain MRI.
Okay, so basically, this paper is from Bruce Fischel's group in MGH, and a guy that works with him, Adrian Delka. He shows up to some of our no-brainer meetings. He wrote this paper and has some overlaps with the brain surface reconstruction stuff that I'm doing, but it's segmentation. But what I've found in a lot of the papers that I've read is that the architectures for performing segmentation are very similar to the architectures performing surface reconstruction. So, I mean, I've always wanted to see if there's a way to do an unsupervised surface reconstruction. And because of the overlap, and because this person is like near our group, I want to read this paper. So, so basically, just like the sales pitch of why segmentation is important. Basically, for diagnosis, which we all know, like tumors and other abnormalities in the brain, strokes, etc., and tracking of like brain atrophy over time. In fact, that's probably something that's closer to our work's usefulness. Is the surface reconstruction gives you better ability to perform those atrophy calculations. It's also reported for segmentation. Why is unsupervised learning important? There's a lot of answers to this question, but the ones that stand out to me are basically the cost of supervision. So the expert labeling is expensive and not always present, and also the bias of the expert labeling. So a lot of the methods that I'm working on for surface reconstruction use free surfer labeling, and whatever biases are in free surfers algorithms will be also part of the training set. But also when humans are doing the labeling, there's definitely biases. So if you can kind of get away from that, that might improve some of the viability of your algorithm. So basically, the interest in Bayesian segmentation is just, I mean, it's just an alternative to deep learning, or it's maybe more traditional approach. Particularly their interest though is, I think this overlaps with some stuff Harsh is doing a little bit, but the need to be contrast adaptive in your methods, basically improving generalizability. The basic premise behind this in general is that if you don't need labeling to do training, then you can, like, if you have some subset of data on a new MRI machine, you can retrain without having the experts relabel and stuff like this. Their contributions are basically, they merge some of the interpretability of Bayesian methods with the speed and speed of unsupervised or deep learning methods. So basically, classical sequential algorithms are kind of slow but prevalent in the neuroimaging, but there's just a pattern of replacing these algorithms with deep learning methods that are more parallel. Yeah. So basically, at a high level, I mean, honestly, this paper in some ways is very easy at a high level, and like a little bit harder to get through the why of it. But at a high level, they have an atlas, probabilistic atlas, that basically has a distribution of like per voxel on like what segmentation label it should be at that voxel location. And they also feed in MRIs. And both these go into a CNN. The CNN predicts a field that the top layer of the network, let's see. This portion of the network handles the deformation. And so basically they predict how to predict this atlas, and they do an atlas deformation, and they get a warped atlas. And this warped atlas, in my opinion, could by itself be a kind of segmentation. In the bottom half of this network, they predict likelihood parameters, which they use to create likelihood maps, which is also kind of like a segmentation. And then they basically like sort of use each of these to like increase the segmentation labels where these two methods agree, and cancel out where they disagree. And so it's just kind of like some level of redundancy between both approaches. Let's see. So this is where the theory starts. So basically, for the most part, this whole approach is, when they say it's Bayesian, I mean, they have a lot of all the equations in the paper basically lead you to having an interpretable result. But for the most part, what they're doing is they're just replacing like they're estimating the parameters of the Bayesian equations. So the segmentation, which is estimated, is equal to basically the mode of this, the likelihood times the prior. And this method is basically called maximum post-story estimation. And this is like just standard statistics. In their approach, the prior is related to the probabilistic atlas, which is used to make the deformations on the atlas. And the likelihood is proportional to the image intensity. So the bottom half of the network where they predict the likelihood parameters is and create these likelihood maps is related to the image intensities. So essentially, they propose the problems. They talk about the parameters theta s, which is label probabilities and atlas deformation related, and theta I, which is image intensity related. And they basically walk you through how they go from the estimation in terms of like the inputs, and then they talk about the estimation in terms of the parameters that they're using. But they quickly point out that this estimation is intractable, so they proceed to replace certain components of this with neural networks. So, I mean, here's where they're estimating the parameters for the deformation and the image intensities. It's another just equation where they need to find the mode of a distribution, and the argmax of that is basically where the parameters would be. Okay, so in general, like you can do all of this without deep learning. There's a standard algorithm called expectation maximization, which can do all of this estimation. And basically, expectation maximization is kind of like a clustering algorithm, where the algorithm is like trying to figure out where the means and standard deviations for the clusters are. It's iterative, and it's one of the methods they compare against. And in this instance, the clusters for the algorithm are basically the segmentation labels. Okay. So here basically they're defining the probability distribution of the segmentation in terms of the atlas and the deformation parameters, and essentially, like they're per voxel, they have that they to get the probability, they just multiply over the voxels for the atlas after deformation. So they also have this parameter that's similar to cortical flow, like some of the proofs in cortical flow, which basically in cortical flow, it's a surface reconstruction method where they do deformations and they use an ODE solver to integrate through this diffeomorphic field, which is basically solving an initial value problem for a differential equation. And in that paper, there's a proof where they basically say that if you bound the change of the solution to the ODE, that you get it by ejection. So like the deformation is invertible. And if deformation is invertible, you don't have topology problems. They don't go into this paper, but basically they have a parameter where they discourage deformations of the atlas from being like too dramatic in one step to make sure the topology is good. Let's see. So this is the bottom half of the network stuff. So basically, concerning likelihood, they pose that the image intensities are all basically like a set of Gaussian distributions per voxel with different means and variances per voxel. And they're setting up the loss function for this unsupervised method. They assume a flat prior instead of something like a softmax, and it's between 0 and 1 because it's a probability. Okay, so like I've said many times, they basically, all of these places where they're doing estimates on this theta parameters, theta s and theta I, they're replacing those estimates, which could be done with like things like expectation maximization with a CNN, which predicts the parameters or the deformations. So the top half predicts the deformations and the bottom half predicts the mu and sigma squared for the like maps. And this is essentially what the loss function becomes for the network. So there's a term here where they multiply like some Gaussian distribution of the image intensities from the likelihood maps over the labels, over the voxels, and over the test samples. They multiply this by the deformation probabilities that you get from this atlas. So the atlas is basically probabilities per segmentation label over all the voxels. And these terms don't multiply together. And the effect of this is that, like I mentioned once before, that when you where these probabilities are like both high, that segmentation label will be accentuated and more likely to be chosen. And when they disagree, like if one's 0 and one's 1, it'll act like a mask and make it so that that zero it out. So basically, like when they agree, that segmentation is more like label is more likely to be chosen. And this is the term for the penalizing any massive changes in one deformation. So, and it's just important to point out that per image, there's a different set of parameters for the likelihood maps. The architecture is 3D UNet, and they use Ricci-Laylow activations, straight up to 3x3 kernels and 32 filters. Standard architecture you see in segmentation and surface reconstruction. So one thing they mentioned is that they, like one thing that I kind of struggled with in this paper, I would say, is like determining whether these likely parameters were per voxel or per test sample. And basically it appears that they're doing a global max pooling operation per sample. So these likelihood parameters are per test subject MRI. They also have a network integration layer.
There's still per voxel, right? Mu is a vector.
Is it? I mean, I wasn't sure that I would think that would be the case, but I just never really. I mean, this global max pooling usually gives you one value over a whole thing, right? So global one.
But that doesn't make sense. All of the labels of all of the voxels are the same, basically.
Yeah, I mean, I think you're probably right. It wasn't clear to me enough to really say one way or the other, but I mean, I thought the way you did, but I also was confused by this global max pooling operation thing. So that's something I wasn't able to really definitively nail down, but they also do that, like I mentioned before, numerical integration. If you're interested, I don't really want to go into it, but if somebody's reading the slides later, I guess I just put it in. But the max pooling operation, and for everybody that doesn't know, basically is like you instead like you're looking over whatever your max pooling filter size is and getting the max value, and that becomes your result. So this is ultimately like the thing that gets optimized, and the label that gets chosen for your segmentation is basically where the Gaussian distribution and the probabilistic atlas are both highest, that segmentation label gets chosen. So in my opinion, basically, it looks like instead of like using an iterative expectation maximization algorithm, they're taking advantage of the optimizer to discover weights that are able to get something that's close to this. And they're estimating the mode of this distribution that way.
So question, some of the like core what is it, the Cortex OD or whatever those methods, they are also iterative, right? They solve thing and then feed it, and so they don't do it here. It's just one.
They don't say that they how many like steps they do in their ODE integration. They do ODE integration, so they could take one step, but it seems like if you wanted to expand this architecture to do it multiple steps, that would be good. In fact, I had a slide in here. I probably took it out, but like basically, it was saying that like one of the ways they only do one deformation or something like this, and one network for that deformation. But like in all of these other papers that I've read, using multiple networks to do, like first network does a coarse deformation, and subsequent later networks do like more refined deformations. That might be a way to improve this method. But let's see. This is just I just put this here in case like somebody like went brain dead over the statistics and wanted to see like a picture again. But yeah, I mean, the architecture is not that complicated. It's just a unit with a deformation and a warped atlas and a unit that predicts these likelihood maps via these likelihood parameters, and creates these likelihood maps. I think that your question is probably explained in equations to some extent, but like. So like, so if J is the voxels, that I would think these mu parameters, like it's not clear to me from this equation whether these U parameters are distinct per J. Like here, you would think it might be because it's SJ, but I'm not sure. I'm just not sure. So they use several data sets, and this is a partition of their subjects. And they use a standard free server preprocessing pipeline, which does like basically recon stuff, which is like skull scripting, bias correction, intensity normalization, icon registration, and resampling. So, and it's kind of like something that's a little bit. I mean, you want to make an unsupervised problem as easy as possible, but the fact that they have to do so much pre-processing to get it there, it's a little bit. I would disappointing that you have to use free server in the pipeline before you can do anything. But because free server takes like 4 to 6 hours per subject or whatever. I mean, I'm sure.
Why are they using again free server pipeline? Because they're taking an atlas and they're taking a C1 imaging, so they don't take anything else as an input. Like, why don't they need free server? From that diagram again, I'm judging just the diagram that you showed.
I mean, I don't know why they're using free server. They don't need the segmentations except for as like comparison after. They don't use the segmentations during training. There's several experiments. Some of them basically go into whether or not this methods you can train on one data set and test well on another. And some of them determine whether there's like how useful this is on small data sets. And they compare the results against an expectation maximization algorithm, because that's another method that considered unsupervised in a way. It's like basically a clustering algorithm. Something that's interesting to me to point out is that, okay, so if they have this deformation field, but it's discrete, they per voxel, they interpolate it between the voxels to get a continuous field of like where to deform the atlas with linear interpolation. And one of the hyperparameters they observe from a validation set is like how much to dampen the change with this lambda parameter of the atlas. And they set it to 10 through all their experiments. And so basically, all I want to say about this is that they consistently do better than expectation maximization, from what I can tell, in most of their experiments.
But the EM is pretty close.
Yeah, it's pretty close.
What about speed-wise? Which is faster, EM or them? Because it's Gaussian, I'm assuming EM wouldn't take so long because of the trigonometrical.
I don't remember the relative. I remember that it only took 15 seconds for theirs. I don't know how long it takes for the
Like I just wonder if we, put EM on GPU, parallelize, etc. Will it be as fast? Probably. Maybe faster.
Yeah, you could probably parallelize expectation maximization on GPU and do good too. Let's see. So basically, there's just some example results of their deformations, which has color schemes that are similar to preservers, color schemes for segmentation on 2 different data sets. So in conclusion, their method is fast, beats expectation maximization, and I was interested because of the deformation approach, as well as the introduction of interpretable loss functions. Yeah, so that's pretty much it.
So if they can take, that's kind of went too fast for me, but that's fine. So if they can take an atlas and deform it, the thing that you started with in the beginning, if they can take an atlas and deform it to the subject space, subject brain, they're done, right? All the segmentation is there. Each voxel.
You could just deform an atlas and have a segmentation.
Yeah, why aren't they stopping there? What else? Like what after that? What are they doing? Doing like jittering those voxels? Like
I think the second path through the network is just kind of like a confidence. I mean, it acts like confidence to dampen certain segmentations from the atlas and to let pass through others that were in agreement with the likelihood maps. So the likelihood maps, like it's basically kind of like a gate from LSTM or like a mask from other things.
While it's doing segmentation, while it's doing the warping, while it's doing information.
Yeah, you take the warped atlas and the likelihood maps and you combine them in order to get the final segmentation.
Oh, okay, so they are independent. So the warping happens kind of based on some geometry, and then there is a separate network that estimates uncertainties, and then you kind of align them.
I think from what I looked at, when I looked at the architecture and what I read, how independent these networks are, I would say probably not completely, because it looks like there's just like the initial part of the network is UNet, but like the final part of the network, there's like a fork to do the deformation and a fork to do the likelihood parameter.
Are they using the same feature space?
That's what it looks like to me. So I've seen some similar things with confidence papers where they're calculating confidence in addition to like a prediction class. That they don't use redundant networks. I mean, but it's kind of like a multitask learning situation, I think. Like where if you're doing more than one type of task, sometimes networks will learn more robustly, even though they're not independent. But I mean, I think it's worth pointing out that the features are from the same network, and us, how much value the second network adds would probably be worth an ablation study, which I don't think they published, so.
But I also then don't understand what is their loss, right? What, how do they?
Yeah, and that's,
like, what they, yeah,
I think the way I interpret it is that the deformed atlas is the prior, and from the T1 scan is the likelihood, and then together you multiply them and you get the posterior.
It's exactly like, yeah, that's exactly what he said.
You parameterize the prior using, I think they share the same network, but you parameterize it using these parameters, the prior, I think. And you parameterize the likelihood using the other flow. And then when you multiply them together, you get the posterior. And what you're trying to do is maximize the posterior probabilities. So the higher the prior is covariating with the likelihood, I think that's their loss function too. Does that make sense? That's the way I was thinking of it.
Yeah, that's exactly right. For every voxel, those are both probabilities. One is the atlas weight, which is the, let's call it a label, and the other is the sampled probability from there.
And then when you multiply them together, you get the unnormalized posterior.
also, this is the objective function, basically.
I mean, this is the important one, in my opinion. The other ones are just like regularization terms. So this is the most important term that, in my opinion. And they say that basically.
So A would be the prior, and this normal distribution, which is the bottom part of the thing, I think is likelihood.
Yeah, A is a function on the atlas.
Right, yeah,
It's a deformation on the atlas. And then the Gaussian distribution, normal distribution is sampling from that learned mean and standard deviation from that label. For that segmentation label.
Argmax is basically just saying, find the mode of this distribution over here.
because it makes sense to think of the atlas as like a prior, right? So it needs to agree with what the actual subject's T1 looks like, so you get like the prior, but like the, I think, yeah.
So normal distribution, the likelihood comes from T1.
Yeah.
Did you include the diagram in the slides, their model diagram?
Yeah.
This? Yeah. There's only 3, I think. So. Yeah, the confusing thing about the loss is just that it's unsupervised, it doesn't have ground truth, which so usually most of our losses are basically like L1, L2, MSE.
I mean,
But you have to understand, it's like what's maximizing, what therefore what the weights are learning, and like why the mode of this distribution is.
do you really think it doesn't have a ground truth or a label or anything?
So yeah, that's something I didn't point out probably through the presentation. The thing that concerns me about this being claimed as fully unsupervised is the atlases, in my opinion, are basically a form of supervision, because like somebody has to get a bunch of atlases, label them, create the probability distributions from them in order to create the atlas, the probabilistic atlas. And so like just to get those statistics requires experts. But if you assume, you ignore that part of the whole thing, then there's no ground truth in the loss function. So.
Yeah, I don't think it's really unsupervised at all, honestly. I think they just get to say that.
But I think
the atlas.
I think it's semantic, like the way when I hear unsupervised segmentation, what I think is T1 as the input and label as the output, and you train it without the labels.
Yeah.
But here, there's a different task, is how to correctly warp an atlas onto a subject's brain. So like the
It's
problem
still
that they're solving is.
It's still
atlas warp.
segmentation. It's still a segmentation job. It's still argmax, right? It's still labeling each voxel as a
Yes.
segment.
Well, but it takes an atlas in standard space and warps it into this specific subject space. So that it's not like, it's just semantics. You can say, oh, this is unsupervised, like this is segmentation, but the problem is different.
It kind of depends on if you think that, for example, we have a lot of atlases, right, already. Right?
Well, I mean, it's a very constrained problem that I don't blame them or anything. That's very interesting. Let's take advantage of what we know.
Right.
But instead of just segmenting any random image, it says we already know it will be this. We just don't know where those regions will be located, and they are topologist friends. What do they call this transformation that it's
Homeomorphic.
homeomorphic? Like the regions can move, but when they move other regions around them. So like just let's take advantage of that and just stretch or deform what we have. But that's like totally different picture than I had walking into this. It's the way I thought it will be done.
I think that you still get a lot of value out of this though,
Yeah.
because like the probabilities in these atlases are probably pretty fixed, and but what this would allow you to do is like when you move to a new MRI machine or like covariance in your MRIs or whatever, then like you would not need any labels on that to fine tune on a new data set.
Well, that's interesting because, okay, could it be, I'm just trying to play example advocate or just being myself, I don't know. Could it be, it's like, remember when they introduced ResNets? We still call them ResNets, but actually what they did is skip connections for gradient flow. This residual talk is nonsense. I mean, it's just to sell the thing, it doesn't matter. It was an auxiliary talk to sell the paper. Then when they introduce DEX, reintroduce, they also talk about unfolding, blah, 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 the infinite network, but it's all just a way to sell the paper. Could it be that all they needed is, okay, how do we stretch an atlas to a brain? We can do it through posterior maximization. And yes, it works. Like, what is our loss? Okay, posterior maximization will get us this loss. And this all Bayesian talk is just a way to sell the brain.
Yeah, I mean, that's kind of what it felt like, but I mean, at least there's some, it's pretty interesting that they at least had some theory on it, but how strong it is.
Oh, no, but
It's just a very.
Bayesian learning has strong theory behind it, and like, it's very consistent. It's a good calculus and everything. Calculus probably. Yeah, I'm with that. But it's just like what problem? The kind of problem that we're solving is probably not to have a probabilistic atlas, but actually getting it done. And one way to look at it. Yeah, you're like.
This also looks interesting to do with flow networks, because then you parameterize directly, right, the probabilities too, which I guess would also be pretty interesting, because then you can really quickly sample as well. And you get a closed form. You get a closed form loss.
I'm a little confused about how do they calculate the likelihood? Do they have to calculate this warped atlas and then use that to calculate the likelihood for each?
No, it's a different path. So basically, like, you need these parameters out of the CNN to calculate the likelihood, and the atlas deformation is a different path through the network. I mean, the network is here, but a different path to the output. So they're completely independent, except for the fact that they have shared weights in the CNN, which is something that Sergey was just asking about, like how much, are using two independent networks or one network that might be branched in a way. Well, it looks like they're using one network that has like the final layers to do different things.
Oh, I get why they're using the global pooling in this case, then global pooling here, because they need the mean and the variance like for the whole label, like MRI. So you can't have specific. I mean, you can't have patches of your unique scales, exactly. So that's why you need, and for that you need the likelihood, direct value of likelihood as well.
It's specifically a global ruling layer.
global, yeah,
Yeah.
sorry.
I don't know if they say that.
Yeah, they say,
Yeah.
we had this,
I think-
we had this doubt, like, why was it like global?
It's because they need a scale.
Yes.
They need mean variance per each label.
But the label, this mu sub L, is the size of the voxels it's in the voxel space, right? It's
You
one
sub
pole.
L, no,
What is it then?
it's per image, per label, it's one scalar. They build a distribution, you can look at the code, they build a distribution based on this average and this standard deviation for each label, and then they sample from that distribution, a probability distribution, for each voxel.
Wait, so mu sub L is a scalar value?
For that label, yeah.
Yeah, sub L, like this, the
Yep.
specific. So they have a vector mu in the label space.
It's
If you
the
put all
vectors
the
of size
mu's
L, yeah.
together, but the labels are discrete, they're not continuous. And they have this Gaussian distribution in the label space.
Yeah,
That's what confuses me.
they sample
Continuous.
probability values. They actually build, in the code, they use the TensorFlow normal distribution object, and then they do a probability sample for each voxel.
Yes, so what is mu then?
It's the average to build the distribution that they sample.
No, physically, what space it lives in?
It's a scalar. Per label, it's a scalar.
No, what is that space? Space of label values, no, it's space of probabilities then, it lives in
Well,
the box.
no. They build the distribution from that mu and that standard deviation. I wasn't clear if they normalized them, but they're just outputs from the model. They're
No,
just-
but what is mu of 0.5? Mu sub L,
So I wasn't clear from the paper if they did anything to normalize them or change them in any way. I couldn't see anything like that in the code, although my reading of it was somewhat cursory. But they're just values, the mu and the standard deviation, they build a distribution from these two values. And then for each voxel, they sample from it.
no,
So-
but that's mechanically I understand, but I'm trying to understand.
I don't know if they normalize the mu or standard deviation after it's output from the model. I looked for that. I did not see if they did anything like that.
Let's,
So basically, they have the deformed atlas, and they have, in the deformed atlas, they have a region like 300,000, well, okay, not 300, 125,000 or something, like some thousands, thousands of voxels that belong to some region. And they say, okay, all of those voxels that belong to some label are distributed like that. The labels, the probability of all of those voxels to having this label goes according to this distribution, regardless whether this voxel is closer to the center of this contiguous region or closer to the end or to the border with another region, which in my view, the probabilities are different of this label being.
So after this n, after you sample from your distribution, you get, for every voxel, you get a vector of values. This vector is of size labels, and this vector sums to 1. So that's what the sampling does for you. That's what gives you the likelihood. It gives you the likelihood values for that voxel for every label. And their probabilities, so they all sum to 1.
Yes, but the distribution is uniform across voxels. It's the same.
Yes, sorry, it's
It's the same distribution for each voxel.
It's the
It's
same
just your
distribution,
sample is.
yeah. Yeah.
And you don't. Okay, the likelihood is the same. It's only, okay, the prior is kind of moving it to the.
I don't know what kind of language you want to use, but yeah, I think.
Otherwise, everything will be just a white noise kind of thing.
It's not, because it's based on that average and that standard deviation output from the model. So I wouldn't call it white noise.
No, but it's Gaussian for at each voxel. Okay, it will not be, it will be white. White noise is that something from Gaussian at each voxel. But the prior, the actual voxel value heavily weighs just one of the possibilities.
Yes. Well, actually, I mean, it is possible that the labels are all fuzzy. Right? That is a possibility. That for that voxel, the labels happen to be close to uniform.
No, but your atlas is not quasi. Your atlas is exact, so your prior is exact.
Go back to the diagram.
Do they get a mu and a sigma per voxel though?
No.
No, yeah, that's what
It's per
confuses me.
image.
That's what confuses
It's per image per label. So that mu and that sigma is based on both the atlas and the image, which are both input to the CNN. It's a UNet, right?
Of course. I don't know any other.
But in the caption, it says they view likelihood maps, which to me reads like.
They build the distribution for that image and that and those labels.
Sure.
And then they sample a probability vector from that distribution. And that probability vector is your likelihood for that voxel for every label.
Okay, so how do you sample that?
TensorFlow dot normal dot sample
I don't know, but
probability.
if you have a vector of 5, let's say 5 labels,
Yeah,
how do you sample a whole image from that? I don't understand that. What do you mean you sample the whole voxel?
so so let's say you have 5 labels, right? You build 5 distributions of just a Gaussian distribution.
No, it's one spherical Gaussian. Imagine
Or
it's spherical.
spherical. Okay,
Imagine
sure.
it's spherical.
Yeah, okay.
Mu doesn't matter.
Okay.
Doesn't matter. It's just sigma, and sigmas are all the same.
I just don't understand the sizes of the tensors. One of them is 5 and one of them is like, let's say 100 by 100. How do you sample 100 by 5? I don't know. You just sample randomly 100 voxels?
Yes.
Like 100 times?
If you have 100 voxels, you just randomly sample from this distribution 100 times.
So the more I think.
Consider
of
it
it,
multidimensional
the more
Gaussian as well, so you can do it as 100 by 100.
Yeah, it's multidimensional in the sense that there are multiple labels, but
Right.
it wouldn't be per voxel. I don't
But it's
know.
not a
if I-
multivariate Gaussian.
Distribution is the same, but number of samples is exactly the number of voxels.
Yeah.
Each time you sample,
But you sample each voxel independently, right?
there are two.
Yes.
Two semantic meanings of word sample. Sample is one thing, and sample is the collection. So the collection is number of
We're
voxels.
talking in the probability distribution sense, though, sample, you sample it independently versus a multivariate Gaussian. I
It's
guess
independent.
But there's only one U and
It's
sigma per
independent
label,
of the
right?
spherical.
No, I don't think so. I think it's a spherical, but it's.
Yeah, it's spherical, they're independent regardless, but yeah.
Not even if they're not.
They sample each voxel independently.
Yeah, so it's axis aligned. It is an axis aligned distribution. You can do the sampling independently. There is no interlabel relationship as they assume, but that's the same as all of them. Bayesian autoencoders, et
Yeah,
cetera.
but it seems kind of odd.
Does it?
Yeah, to me, it seems way more likely to multiply per voxel.
No, but what happens is you're in a label space. For each voxel, you can have one of any of the labels. So imagine you can have 3 labels. I can draw it.
Yeah, but I think he's saying that you sample independently, you have one for a whole image.
You have one average.
Yeah,
one
the
standard
distribution is the
deviation.
same.
Sure.
So you're saying, okay, I'm moving here. And then I'm sampling around it. Or I'm moving here and then I'm sampling around it. It's like give something, but your first step in the give something is defined by, so, okay, give something is a good idea. So you have this one dimension that is cardinality of labels. And you have L dimensions that each is cardinality of 1. So your overall dimension is L plus 1. So this plus 1 has L values. You're doing give something, choose a value here, but you're not doing give something, this value comes from here. It's not sample, it's the atlas value. But we're treating it as probabilistic. So this value comes from here, you're saying I'm label this, and the rest are sampled around it. So that's what I'm saying. You're making the first step in the direction of label, and it's discrete and it's only that label
Right.
value. And then you're sampling around it by saying, okay, well, other labels could have been also true with that probability.
But that's during inference though, right?
Yeah,
Yeah, okay, I was thinking about the training part, I was like, why would you sample it?
Well, the training part, you just maximize.
Yeah, you just multiply them together and you just.
Yeah, so it's a widget, it's not actually, like, this is, it's not true or like
Sure.
not even close to true. It's a widget to,
But this is the training part, right? This is not the inference part. What you're explaining,
but you are doing inference to do maximization.
so
You're doing the forward pass
You're doing the
anyways.
maximization first.
You're doing the forward pass. That's the forward pass, that's.
Yeah, but you don't sample in the forward class, right? You just multiply mu L times A. essentially.
mu L times
Yeah, you
A.
just multiply mu. so
Right,
It's just a
right.
normal distribution that you multiply with A, right? Or no? But that's what I'm thinking, you could also do it per voxel, you could parameterize mu and sigma per voxel, like, that's what they do also with VAEs normally with the reconstruction. And then you can multiply per voxel, right, the mu and the sigma, and then you have an even cleaner posterior, because then you have a posterior over every single voxel. Directly with a better, like a more parameterized likelihood. I guess this is the first step, I guess you could also do.
But
it per voxel.
then you don't even need to sample, right? You can just output that image, because these mu's and sigmas are per image.
You still need to do it per prior, right? You still need to multiply the prior.
Yeah, but I'm saying you wouldn't need that. You wouldn't need to sample at all. You can just output, you can just have, instead of outputting a mean and average, you can just have your CNN output a
And
3D.
you have some confidence
By
interval
L.
now. You now have some confidence interval for each of the voxels, right? Because you have a sigma, so if your sigma is super small, you have a lot of confidence on the fact that this is the exact value of that. That's the way. Yeah, I don't know, that's what I thought, because I know people do that in other things sometimes, that's why I was confused, but yeah, this also makes sense.
The code probably could help a little, but no, you're the only one who looked at the code.
Right,
You did.
I did. I looked at the TensorFlow code. It was-
Yeah, they're all kinds of fun.
No, they have a PyTorch implementation.
Well, it's kind of
I didn't
moving to PyTorch there,
I found it harder to read.
so. All people.
Very cool though.
Yeah,
But beyond the fact that I don't really think it's unsupervised, I actually think it is a really cool paper and really useful. I don't know if he's on the call, but there is an expert on this, Hirsch. His,
no, he's not.
since that work is.
Delta showed up a few times though.
Hmm?
He showed up a few times. Not Arch, but Delta, the author.
Oh, for the no-brainer, yes.
I was thinking of the other call.
Yeah, we can ask, sorry, Adrian, or we can ask Harsh to ask Adrian, we can, their own like. One question, I think Adrian is even on that, no-brainer slide, MIT slide. Questions can be addressed there. Yeah, it's interesting, but it's kind of also confusing at first, but then, oh, okay, this is what they're doing, not the actual unsupervised the way I thought of it, but it doesn't mean that my way is the right way, but it's just like I was totally thinking differently.
A long time ago, maybe like 2019, I wrote some papers on like confidence with like classification, and it just seems like these likelihood maps and the end, the Gaussian distribution here is saving just like confidence, but they've got a lot more theory behind how they're using.
That would also make sense that they could even do expectation maximization, because they only need to parameterize with a few parameters.
Well, it's the original process is just, yeah.
No, I know, but I'm saying like, right, that makes sense because you only have you have fewer parameters than I initially thought they had.
Yeah, they basically took EM and parameterized it with the big old neural network.
But so, yeah, so the next step, one of the next steps could be to do it per voxel. I think, because that's what you can do now. That's definitely, you can definitely do that with EM, because that would be way too many
Unbelievable.
parameters. Like, very cool.
Okay, thanks, and See you next week.